Okay, so welcome to the last talk of this long day of DEA workshop. I'm pleased to introduce Pedro Montealegre, who is a assistant professor at the Universidad Adolfo Ibáñez in Chile, who did his PhD in France in Orléans, and who will tell us about compact local certification for graph classes.
Thank you, Laurent, for the nice introduction and for inviting me to this workshop. And also thank you all for staying for this very last talk in the evening for you. For me, it's the afternoon. Okay, so let me switch slides. Okay, so my talk is about graph classes that are useful for the design of efficient algorithms in the context of centralized algorithms, but also for distributed algorithms. Some of these classes are useful for real world cases, like we saw in this talk, like planar graphs. Interval graphs, for example, are useful for problems related to scaling and so on. And other graph classes like Chordal graphs are less like real world inspired but they are like general enough to contain many important graph classes. So sometimes they have very nice like properties that one can exploit to design efficient algorithms, right? So in fact, many of these classes there are many, but many of these classes are used in distributed algorithms. Today we already heard about that, but I want to mention like some examples for planar graphs, like for finding or approximating minimum dominating sets, MSTs, minimum cuts, computing fast DFS or computing the diameter quite fast. This also is the case for interval or chordal graphs, where we can compute quickly a coloring, a maximum independent set, or there are some results regarding Byzantine agreement. For many of these problems are exact solutions or sometimes approximate solutions. So there are also these graph classes are also used on the distributed context, right? So in all these examples, the input graph has, or the problem has the promise that the input graph belong to this class, and we work when assuming that is the case. Even in the examples below, they assume that an interval representation of the graph or a click tree, I will explain that in a few moments, is given in the input in some cases. So we ask what happens when we run an algorithm that is dedicated to a particular graph, but the network is not in the class. So that could be very problematic, because that can give us erroneous outputs, like with no guarantee of the approximation algorithm, for example. We can obtain lack of termination. We can wait for a message that never arrives or something like that. And as I said, some algorithms require that some information is given, like a planar embedding or intersection model or tree decomposition. So we cannot, if we don't have this information, we cannot even run the algorithm. And the bad news is that many of these graph classes, the natural graph classes, cannot be recognized by local decision algorithms. So they require a lot of rounds. So this is somehow problematic, because the classes cannot be recognized, and no question about computing for example, intersection model or the planar embedding. So to cope with this problem, we can ask for local certification with one of the perspectives. So we have like in the context of proof labeling scheme. So we can imagine that we have like a very big computer that is aware of the whole network and can help the nodes with a labeling that will help them to decide if the graph belongs to the graph class that we're studying, right? But the nodes do not trust these big computers, so they want to verify their certificate, so they can share messages with their neighbors in like a one round. They can see their certificates, and with that information, they have to decide whether they think that the graph is in the class or not. Okay, they have to agree or reject. And we say that the graph, we need that the graph is in the class, then everyone has to accept, and if the graph is not in the class, then someone has to reject. So formally, a proof labeling scheme recognizes the class X if there is a local algorithm such that if the graph is in the class, then there is a labeling where every node accepts. And if the graph is not in the class, then some vertex rejects the graph for every possible label that the nodes are received. Okay. So I think that many of you already know this model, but I will just give a simple example to fix the idea. So suppose that we want to check if the graph is a path. So nodes can the labels are like a distance to a root simply, and then the algorithm is just to check if the degree is 1 or 2 and interpret the labels as a distance to the root and check the consistency. So they have to have a neighbor that is closer to the root and one that is farther to the root. So in this case, everyone will accept. And obviously, if the graph is not a path, then there's no way that there's a labeling that can convince everyone, right? So, for example, where there will be here 2 vertices that will see the same label or the same distance to the root. So, what? Let me give some. So, how we measure the performance? We measure the performance like in terms of the certification size. Like this is the minimum size of the label that can be used to recognize a class under the conditions that I gave. So obviously, to recognize any class or any property of a graph, we can. Oh, sorry. Oh, why cannot go back? Let me. So if you want to recognize any class of graphs, you can just give like the whole graph to every vertex, and then they can check by themselves. If we want to recognize trees and paths, this is the classic based paper of a proof labeling scheme. They show that log n bits are enough and required. If you want to check the diameter, we require order of n bits of certificates of order of n bits. The tilde here is hides, as always, the logarithmic factors. And another obvious example is like, for example, the chromatic number fewer than k. It's easy. The nodes are given just the colors, and they check the coloring is proper. But for example, checking the chromatic number greater than 3, it's quite hard. They require like essentially receive all the adjacency matrix. Okay, and I mentioned graph of bounded degeneracy also require like log n certificates, and that's enough. This is just giving the decomposition order, right? So I've been working for a while in the certification of graph classes with different people, and the idea is to obtain like efficient certificates for like well-known classical graph classes. And I just here want to present some of the results that I have obtained with different colleagues. So, for instance, for all these classes listed here, we show that log n bit certificates are enough and required to certificate these classes. One example is planar graphs. Another example is graph of bounded genus. Another is chordal graphs. These two works have been done with Laurent, with Pierre Fregnault, Van Rapaport, Eric Remila, and John Todenka. regarding chordal graph, interval graphs, and circular R graphs, I will explain this later class. Is a work that I have done with a master student, Diego Ramirez and Ivan Rapaport. And very recently, I have worked also with permutation graphs, trapezoidal graphs, and other families related to this. I want to and maybe the message of this talk is that even that it is not it's not too complicated, I would say, to find this to prove this results, but each one of them requires like an ad hoc algorithm. There's not a general thing that we can use for every class of graph. We just have to look to the class of graph and find a right characterization that allows us to build this smooth certification. I will illustrate that with these 4 examples. Okay. So just before that, just let me give an idea of why this certification is not trivial. Okay, so for example, consider a PLS for planarity that just gives the coordinates of the planar embedding of the vertices, and suppose that we wanted that the vertices just check that the edges don't cross. The problem is that the edges that cross can be very far away in this graph, and the vertices have no mean to know if a crossing edge is somewhere far away in the topology of the graph. Similarly, for example, for certifying interval graph, it is not enough to give the intervals, right? The interval representations of the vertices, because the nodes have no way to know if, I mean, simple as giving the intervals of the vertices. The nodes have no way to know if the referee or if the prover gives them just this, for example, the same interval for 2 different vertices, right? And just communicating with the neighbor, so they can make them think that they are in an interval graph when they are not. So, for instance, for showing a PLS for planarity, we obtained like a 2-part protocol or certification. First, we showed that we can certify a specific class of planar graphs that is path outer planar graphs, which are like a path where no crossing edges in the top of these vertices. So graphs that admit an embedding like this. And the certification for this class of graphs is quite simple. The label must be like a rank, an order of this path, and the name of the edge above each of the edges, so of the nodes. For example, here node 5 has the edge 4, 6 over here. Okay, and similarly, and we also give like an edge, an existent edge for the extremes, right? For example, here the vertex 4 here has the 1/8 edge over it. And just checking it, I won't go to the details here, but just checking the consistency of these certificates is enough to verify that the graph is outer planar. We cannot trick the nodes, make them think that the graph is outer planar if they certify if they check these certificates. Essentially, the idea is that if the graph is not path outer planar, then it's not clear which at least for one vertex, it would not be clear which edge is above of him, and for any choice of this in this ambiguity, for any choice, someone will see the inconsistency. So this is fairly simple. And this is the first part. I won't go to too much detail here, but and in the second part of the proof labeling scheme for planarity is to reduce any instance to a path outer planar graph. So we take a graph, we construct a DFS transversal, which is like a path that is a tour that visits all vertices in the order of a DFS. And then we show that using that we can transform any locally transform any planar graph into a path outer planar graph, which has a property that if this new transformation is path outer planar, then the original graph was actually planar. So this is roughly the idea. If you want to see more details, I presented this work in POTSI last year. So there's a video somewhere in YouTube. So let me talk about now about Chordal graphs. Roughly the Chordal graphs, as you might know, are the graphs that have the only induced cycles are cycles of length 3. So any cycle of length greater than 3 has a chord. And another characterization that may have these chordal graphs is which is called a click tree or intersection model of a tree. So there's a tree, and we can interpret each vertex as a subtree of this given tree. So, for example, vertex 5 is this small subtree, vertex 4 is in red, and so on. And two vertices are adjacent if their subtrees intersect. And also we can see that this construction, in fact, is a tree decomposition where each of the backs of this tree decomposition are maximal clicks of the graph. And that is useful for the design of a proof labeling scheme, because the idea is roughly this: we can root. We take the click tree, we root the click tree in one of the vertices, then enumerate the backs, pick a leader for each back. Here we have to be very careful because the same vertex can be in many backs, so we don't want to make one vertex the leader of many backs, because they will be in charge of checking that this part is a click. So we will have to choose like a nice or a good tree decomposition that allows us to pick like a few leaders for the vertices in a way that we can like spread the information in a nice way. It's a technical detail. And then for each vertex, we simply call V the leader of the topmost back that contains V. So for example, for vertices 1, 2, 3, they see the leader is 1. For vertex 4, its leader is 2, because it's a chosen leader for the maximum back that contains it, and so on for the other vertices. So we keep like the set of vertices that after that back disappear. Okay, the topmost back in this construction. So and also we keep the depth of these parts of the back. We call the depth of a vertex, like the depth of the back of this specific back that we picked for every vertex. And also we will give the vertices the size of this back and the size, the number of vertices that are that have this back like the topmost one. And we show that essentially with this information, every vertex can check if the consistency of this click tree. Essentially, what they have to check if they are a leader, they have to check that their bag form a clique. They can do that with the size of the bag, and also, for example, if the kind of consistency that they have to check is, for example, vertex 2, which is in the topmost bag, sees vertex 5, which is in the bag in depth with depth 2. So vertex 2 also has to check that he sees this vertex sees all the leaders in bags between the path that connects these two bags, and so this can be done. Because knowing 5, he will know the size of the bag, and he will be able to see all the vertices in this path. Roughly, if we and this is interesting because with this construction, nodes learn their subtree, their subtree that defines this intersection model, which is used in one of the algorithms that I mentioned at the beginning. So this certification will be also useful for that local algorithms. And essentially, why this works is because suppose that the graph is not chordal, so we have like here, for example, a long cycle, then somehow the node, for example, 10 or the node 1 will see that there is a connection between it's adjacent to a node in the root or in the node in the vertex of depth 3, but they will not see all the vertices in the path that connects them because this large induced cycle implies that, right? So with this certification, they will be impossible to fool the vertices, to make them believe that the graph is chordal. Oh, I'm running out of time. I will be like a little faster. So for interval graphs, we can use this construction like very, very easily, just because an interval graph can be seen as a chordal graph where the clique tree is a path. So we just use the certification for chordal graphs, but also we check that the given clique tree is in fact a path, and that's all. It's the certification here is fairly simple. So an interesting point here again is that, as I said in the last slide, with this construction, with the verification, the nodes can learn also their intervals. So again, we can use that in the local algorithms that require this certification, this information. Let me finish with a fourth example of an interesting class is circular arc graphs. There are like interval graphs. They are similar to interval graphs, but instead of in a real line, it's in a circle. So we can have like periodic intervals. Okay, so this class is also inspired in scheduling problems where we have to like we have like a periodic program we have to check, and in this case it's interesting also because this is not a subclass of chordal graphs. It's a very quite different class, but also is known because many hard problems can be solved quickly, at least in the centralized setting when the input graph is circular arc. And the certification of this class is quite nice. It's quite simple because there is a characterization of its adjacency matrix, which is called the quasi-circular ones property. A matrix with ones in the diagonal has the a 0-1 symmetric matrix has the quasi-circular ones property if it has ones in the diagonal and all non-zero coordinates can be covered by brackets. I call these brackets like this L-shaped sequence of ones. So you take the first, to start with in the diagonal and look for the first 0 in the row, and this forms since it's symmetric, this forms like an L, an inverted L, and this can be periodical because of the property. So you can like go around this modulo n. So we say that a graph has the quasi-circular ones property if a matrix has the the quasi-circular ones property if every one in the graph can be covered with these brackets, okay? And a graph is circular arc if and only if it admits an ordering of the vertices. We can arrange the vertices of the graph in a way that if we add the diagonal, once in the diagonal, the matrix has the quasi-circular one property. So the certification is quite simple. We define we give the ordering to the vertices, and such that the graph has the quasi-circular one property. We give the size of the bracket, so and then they check that no one in the matrix is missed by anyone. And the hard part in this construction, in fact, is to prove that we can check the ordering, because the permutations are quite complicated for PLS. So, okay, I almost ran out of time, so let me give a conclusion of this talk. I didn't talk about lower bounds. Unlike upper bounds, with lower bounds are there are like a few techniques, and you can almost like build one proof that then you can adapt to any of the graph classes that I spoke before. So there you can like unify the arguments. That's nice. Also, it's interesting that if we allow more rounds of interaction with this server, with this model of distributed interactive proofs, where the nodes can challenge the prover with a round ring, and they have to verify with a good probability, then there are many other graph classes that we can verify fairly easily, including co-graphs, distance hereditary graphs, unit square graphs, and many others that I prove with my team. And there's here a question that I want to propose that we discussed in one of our articles we have with Laurent, whether this we don't know if every hereditary graph class can admit an efficient logarithmic sized proof labeling scheme. We don't know yet any counterexamples, but it's quite hard to think like a proof for this. And this is like I believe that is a very interesting question, because somehow it would somehow imply that all these arguments that I gave in here can be unified to if it's true, right? In a simple argument that allows a PLS for every hereditary graph class. Another weaker question is whether every graph class that can be defined for an intersection model of simple objects can admit an efficient PLS, and that's also unknown for the moment. Well, that's the presentation. Thank you very much.
Thank you, Pedro, for for this nice talk. So, are there questions while we see the extraordinary landscape of Adolfo Ibáñez University? So if yeah, sorry, go ahead.
Okay. So to go back on your last open question, so you said it's open, whether for every hereditary graph classes you have this efficient local certification. Are there examples of graph classes for which you don't know yet?
Yes, I mean, for example, you can imagine, I could say, for example, unit disk graphs, for example. I have no idea how to prove an efficient PLS for such a class. I've been working with my students with circle graphs or polygon circle graphs or K-trapezoid graphs, and for those classes we have PLSs with interactive proofs with more than with 3 rounds or 2 rounds, but having and we don't know how to reduce the number of rounds in many of those cases. Yeah, so I would say in the opposite way. I think that which I know is what I said in the talk. Like any other graph class, I have no clue yet.
Okay, thank you.
So I also have a question. So I'm curious about this thing about like circular arc graphs that you had. This thing with the matrix, like is the order that you have, like this V1, V2, blah, 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 is it the same order, like cyclic order as along the circle, or is it completely different, or?
You can, I think that it's, yeah, no, it's related with the one that you have in the circle. In fact, you use that in the proof. You can see that, yeah, you can see that in the construction here. But
okay,
yeah. You can so you can put like if I remember correctly, you can put like points that start clockwise, and then you put the vertices in the rows of the matrix. Okay. The construction is fairly simple.
Okay, nice. Some other question for Pedro? Well, if not, I guess we'll stop there. So
thank you very much.
Thank you, Pedro, for the nice talk. Thanks to all the speakers, I mean, of the session, but also of the workshop in general. It was very nice, like a bit tiring, I guess. We had a kind of a packed schedule, but at least to me, it was very interesting. Well, some organizer had to leave, so I don't know, Alexandre, if you want to say a word.
Well, thank you for all of those that are still there. And if you have any questions that you would like to ask some speakers that have already left, feel free to send us some messages, and we will keep you informed once all of the talks will be published on YouTube. And yeah.
I guess that's it.
Thank you very much.
So thanks everyone, and yeah, see you for real sometimes in the future, hopefully.
Hopefully soon.
I hope so, yeah.